All right, guys, here we got our last section of chapter 7, section 7.5. Last time taking notes for the semester, last video of the semester. I'm going to go right into this vocab word equilibrant. It's an opposite vector, which is the same magnitude but opposite direction of a given vector, and usually the resultant vector in problems we're going to do. And so very first one, find the magnitude of the equilibrant forces. So there's that vocab word. Of 48 newtons and 60 newtons acting on point A. So what I'm going to do is I'm going to draw point A here. And I have a magnitude of 48 newtons going one direction. Angle between forces is 50. The other one is 60 newtons, so slightly longer. Angle between them is 50. So here's the beginning of my picture. Again, what you can probably guess that we're going to do is we're going to end up making a parallelogram out of this thing. A lot of the problems in this chapter have to do with parallelograms, so don't be afraid of them. And we're going to do our resultant force. Just keep in mind that because I have a parallelogram here, if this angle is 50, I can also figure out what that one is. It is 130. And remember, our resultant goes right through the middle, like so. And so I have this thing called the equilibrant actually coming out this direction. But it's going to be the same length. I just ran out of room, so I didn't draw it all the way, but that is going the opposite direction of my resultant force, which is this. So equilibrant goes this way. The question is actually asking me to find the angle between the equilibrant force, which is this, and the 48 Newton force. So this is what I'm solving for. Okay, so that is the picture that goes with this problem. What I'm going to do is use law of cosines to solve for x right here, and that is going to use the 130-degree angle. And then what I'm going to do is then use law of sines to find this angle. Because remember how that 50, we talked about this in class yesterday, the 50 is not divided in half because these sides are different lengths. So it's not a rhombus. This 50 is not broken into 25 and 25. The problem will be done if that were the case. I need to find this angle so that I can then subtract from 180 because that's a linear pair to find the answer of the question, okay? So I'm going to do law of cosines first so that I can find this side, because then I'll be able to do law of sines in order to figure out that green angle, which will then give me the red angle. Okay, so very first part, I'm going to do law of cosines. So the magnitude of x squared is 48 squared, and 60 squared minus 2, 48, 60 cos of 130. That gives us a value of the magnitude of x being 98.01. So remember, that is here. That is the length of that resultant vector. So now what I'm going to do is I have this triangle. This top one is what I'm going to work with. And I have this angle and this side. I have this side. I need to find this angle. So what I'm going to do now is do law of sines, excuse me. So what I'm going to use is the x value that I just found, 98.01 over sine 130. And I'm going to use the side of 60 over sine of, I'll use alpha. I already used an x, so I didn't want to use another x. So now I just cross multiply and I end up with this alpha thing. The green in the picture is 27.97. You can check me by using your own calculator there. And so that's the green angle, remember, and the question is asking me about this red angle out here. So now that I know this one, I just subtract from 180 to find this obtuse angle out here. So this means the theta that I'm looking for, 180 minus 27.97, gives us 152.03. So this is our final answer, okay? Just make sure that you've got an ability to draw that picture because it's a little bit weird with this new vocab word equilibrant, okay? Now I've got something real common here. This thing about a force of something required to keep something from sliding down a ramp inclined at 20. Okay, so I've got this 50-pound wagon. I've got it on a ramp, and the ramp is a 20-degree angle. So I'm going to actually draw my triangle like so, make it look like a ramp, right angle there. This is 20. And I've got this wagon sitting on it, and the force of the wagon, which the force of a wagon, like the weight of a wagon, is kind of the same thing as like the perpendicular to the ground, kind of like gravity, how it forces you down to the ground. So I'm going to label that the 50. So the 50 is the force of the wagon, the 20 degrees is the angle here, okay? And what I'm going to do, so the force is actually the force acting on this wagon this direction in order to pull it to prevent it from sliding down the ramp. And what I'm also going to do is make this new triangle down here, and I'm going to make this parallel line. This is the same force as it is up here, and that's what I'm solving for. So I'm going to leave an F like that. So just keep in mind that when you have an object on a ramp like this, the force or the weight of the object is perpendicular to the ground, so it drops straight down, making a 90-degree angle. And the force is pulling it so that it doesn't slide down the ramp. And so in order to complete a second triangle here, I drew the force here, and I also copied it down here. We're trying to make a lot of different parallelograms in this chapter. But what you can see is that I am going to complete a triangle right here, and I'm going to drop that line so that it is perpendicular down there. So here's the weird part. What I need you guys to recognize, I'm going to zoom in on this picture. This is how all of these ramp pictures are going to be drawn. But do you see an alternate interior angle here with this one? So kind of turn your paper to the side. Those two blue lines that I have highlighted are parallel lines, which means we have some alternate interior angles there. And so if those two angles are equal, that means that this angle, the 20, goes here. Okay, we have similar triangles here because they have two of the three angles that are equal. This is a right angle because I dropped it perpendicular to the ground. So I have right angles, I have alternate interior angles. That means the 20-degree angle can go right there. Okay, and so it's asking me to find F, which is this part right here of the triangle, the blue. And so all I have to do, I have one angle, and I have this side that I labeled that I kind of covered up. It's 50. And so this is what I'm trying to find, the F. So I'm just going to use regular trig, and it's a right angle, so it's going to be a simple equation to solve. I'm going to use sine of 20, and that is the F, the force, which is the blue, over the hypotenuse in this case, which I labeled 50. So all I have to do is solve for that and use the calculator, and I get a force of 17.101 pounds. Okay, so I've got one more problem that is a very, very similar picture. It's another force, it's another incline problem, so we're going to practice that. I'm going to draw another inclined triangle. I'm going to make it a little bit bigger so it's a little bit easier to see. Right triangle. The force of 16 pounds, so that's the force in this case, and it's required to hold a lawnmower. I'm just going to put a dot for the lawnmower instead of trying to draw a lawnmower. And the lawnmower is 40 pounds, so that 40 pounds drops straight down. I'm going to label it out here. And the force is 16, so the force is this direction, 16, and it's trying to prevent the lawnmower from falling this way, so it's pulling it this direction. I'm also going to draw that parallel down here, that's 16. Okay, so that I can look for my alternate interior angles. And then what I need here is to create a right angle triangle. I'm going to drop that down there. Okay, so this is how all the pictures are drawn. This is asking me to find the angle of the incline, which is here. And so if you remember, I have alternate interior angles. That's why I use these blue lines in order to make my force. I have this alternate angle is equal to this one, which means since I have right angles in both of these triangles, that by default, this angle has to equal this one. And so really what I'm trying to find is this angle in this little triangle here. So again, I'm going to use sine because this is the angle, this is the opposite side, and this is the hypotenuse. This is the same exact picture that I drew earlier. We were just given different information. So in this case, I'm going to do sine of x equals 16 over 40. That means x equals inverse sine of 16 over 40. And that gives me a degree of x equals 23.58. Okay, and that's degrees, by the way. All right, so those two pictures for number 2 and for number 3, those are the same exact picture. You drop your angle straight down like so, perpendicular to the ground, so it makes a right angle there with the ground. The force should be a parallel line that you draw in 2 different places. Connect that so that you have a right angle triangle, and then just notice that we have angles that are equal here due to the AIAs that are there. So those pictures are both the same, and that's how you'll do all those incline problems, okay? All right, I only want to do one more. It's a bearing problem. A ship leaves a port on a bearing of 28 degrees. So remember that bearings are always drawn from north clockwise. So 28 degrees means the ship is going this direction, 28. And it travels 8.2 miles, so I can label that 8.2. Let's see, the ship then turns due east. So it goes perfectly to the right, this direction. So that means this is a 90-degree angle. Okay, just put that in there. And it travels 4.3 miles, so this is 4.3 here. And the question is asking us how far is the ship, which is now here, from the port, which was the starting point. So I can connect this triangle like so. Okay, so I have a little bit of information that I need to use here. The 28 degrees is not inside the triangle, so that's not helpful. And also I'm pretty sure that this is not perpendicular, so this is not a 90-degree angle here. So this angle is going to be hard to find. What I'm going to do is zoom in on this, because what I can do is continue this dotted line like so, because right here I have alternate interior angles. So this is 28. We're always looking for AIAs in this case, and the bearings always have north-south lines like this to help guide you. And so now I think I know that angle because this is also a right angle. That makes this entire angle right here, 90 plus 28 is 118. So I now have that, and I think that helps me be able to do law of cosines to be able to find this side. This is what the question is asking us for. Okay, so this entire angle is 118 because it's 90 plus 28. Okay, so now really quick law of cosines. After I've drawn the picture, it should be a really simple question. So I have x squared equals 8.2 squared and 4.3 squared minus 2, 8.2, 4.3. Don't forget to square root the entire thing after you get this whole thing typed into your calculator, cosine 118. This is going to give us a value for x of 10.9. I'm going to put little absolute value bars because it does, technically it is magnitude. 10.9 miles. Okay, so that's how far is the ship from the port. That takes care of question number 1. What is its bearing from the port is the other question. So in this case, what I'm going to do is, now that I have a lot of info about this triangle, I can use this angle and this side, and I can use this side to help me find this angle. And then all I'll have to do is add to the angle we were given, the 28, to figure out the bearing from the entire angle. So I'm going to find the blue angle first. So I'm going to do 10.9, which is what I just solved for, over sine 118. And I'm going to use the 4.3 side over sine, I'll use a y, just using random variables here. And this ends up giving me a y degree, and remember y is right here. It's that blue angle of 20.38. And so in order to figure out the entire bearing right here, I need to add the 28 to it. And that gives me 48.38 degrees. Remember, that answer right here is from here to here. So that was a little bit of review of bearings, law of cosines, and then again, law of sines, okay? That is all, you guys. I'm going to skip example 5. You're finished. Have a great night.